In this lecture, I want to focus some more on the PV diagrams and some of the nuances of them. So in the last lecture, we talked about the isothermal reaction, or the isothermal process, which basically said that if you had a P and a V, it was proportional to another P times another V. And the reason for this was because, there was no change in temperature. So the change in temperature being 0 meant that the change in internal energy was 0 also. And with P times V being proportional to the temperature, if P times V is proportional to T, and T doesn't change, that means that I can do a P1 times a V1 is proportional, or actually equal to, P2 times V2. So this, I can make this into an equals 2 sign. And what this means is I had put out some basic sort of marks here, and I'll use, let's do this in terms of atmospheres. The units don't really matter because it's all proportionality. So we can do 1 atmosphere, 2, 3, 4, and we'll do over here for volume, let's do liters. There's no reason to do anything else really, so we'll do 1, 2, 3, 4. So I've got this basic setup, and one of the things that we can use PV diagrams to tell us is what the temperature is like. So let's say that you have a pretty cold material. Well, a pretty cold material in a high volume container is actually going to have a pretty low pressure. So let's say that at a high volume of 4 liters, we have a quarter of an atmosphere of pressure. And so then at that winds up being 1. So at 2, the product winds up being 1 if I have some of my cold PV is going to equal 1. So I have 4 times a quarter. I could also have 2 times a half. I could have 1 times 1. And it's just going to continue this trend. So my cold one's going to look something like this. And I could have a hot one. And for my hot, I might have P times V equals 4. And this might be a little too close to that one, but I can have a 1 times a 4. I can have a 4 times a 1. And we get something that looks like this. That one shouldn't curve back. It should continue in that direction. And you could have ones in between there as well. You could have ones even hotter than that. Up here, even hotter. You could have ones even colder, and so on. And these lines that represent where the temperature is the same are called isotherms. Okay, so this word isotherm tells us that the temperature is the same at every point. So the temperature here, 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 they're all the same temperatures. What does happen, and what is useful, very useful, is that if we go this way, the temperature is increasing. If we go the opposite way, the temperature is decreasing. And the reason for this, hopefully it should make sense, is that if you have the particles inside of a container, and you should always refer back to particles in a container. So I've got some particles in there, and they're bouncing around and so on at their various speeds, but on average at certain speeds. And you can imagine that these particles, because this is a pretty small container, they're able to hit the sides of the containers pretty frequently. But if I put them in a much larger container, these same particles going the same speed, same number of particles, there's going to be far fewer collisions with the surface, which means that while the volume is greater, the pressure is considerably less. That's really what this relationship is trying to get at for us. So we start off and we have a lot of volume but a very low pressure, and what that tells us is that the temperature is low. If I go up to this isotherm, the volume is the same, and let's assume that we're using the same number of particles and of the same type. And so with a same volume, same number of particles, same type of particle, if we're getting a larger pressure, then that's indicative of a higher temperature. They're moving much more rapidly. That's the only way that they're going to be able to apply more force per area to the surface of the container. And this one likewise is even hotter because they're moving even faster, so they're able to hit the surface with more force and more frequently than they were before. So that's the basic idea behind this PV diagram and the isotherms. And the isotherms are very useful. Typically when I'm drawing PV diagrams, I typically start off by sketching in some isotherms based on some of the relevant information. Now there are some more things that we can do with PV diagrams, and I'm going to show you one of the main ones in just one moment. Alright, I have a fresh PV chart for us to work with here. And what we're going to do is we're going to relate this pressure volume chart diagram to work. So if we think about what we had previously said, if you have pressure times a change in volume, you get work. Because this is, of course, force per area times distance is none other than force times the distance, which is exactly what we expect when we're looking for the work done by the force that's in question. And when we're looking at a PV diagram, this force is the force exerted by the gas. Okay, so this force is the force that's being exerted by the gas on something else. And we're moving that something else. In most cases, we think about like a piston or some sort of a platform holding weights, that type of a thing. So we have this distance that the force is acting over, and we get work out of it. The question is, how do you use a PV diagram to help you determine how much work is being done? So let's use an example of a cold, maybe not as cold as our previous example so that we can see what's going on. But I'll start at 4 and 1 and 1 and 4 so that we get the same product the whole time, and that'll mean that we need a 2 and a 2 in there as well. And so our PV diagram looks something like this. And graphically, this pressure times the change in volume is actually going to be the same thing as for those of you in calculus, the integral, or the area under the curve. So let's say that I want to find out how much work is done. Well, first of all, let's go with something else. You can't just draw the line. You also need to know what direction the process is taking you. For instance, are you expanding the gas, or are you compressing the gas? So let's just do a quick little sketch up here. So we have a little container. And we'll make this the load-bearing part of it here. A couple of weights. And let's expand this. So we're going to take this and we're going to expand it upwards. So our delta x is upwards, which means that our delta v is going to be increasing. It's going to be positive. And so if you look at your chart, if you have an increasing volume, that's this way. So increasing v. I know that my writing is illegible. This is also expansion. Okay, so we're expanding the gas if we're going this way. This way would be compression. Compression. And in our case, let's say that we're expanding it. Okay, so what's happening then is that the gas is doing positive work on something else, which means that the gas itself is losing energy from doing work, but we're also providing some heat. So we're putting some heat in to this situation. And so our process is running this way. Now, if you look at this diagram, what you can do is you can say, well, let's find the area under the curve, because that's what this is. It's saying take the pressure times the change in the volume. And that's what area is. If you're in calculus, that's the integral. So if I go from, I think I drew it here, it's a little bit off, but something like there, over to here, and say this is where the process ends, then I can just find the area under that curve to tell me how much work is being done. In practice, this isn't necessarily very easy, if you don't know calculus, then you'd have to kind of guess. Luckily, a lot of times I might say, let's label this point A and this point B. I might say that the heat exchange from A to B is positive. I don't know exactly what the number is, but let's go 6 joules. And so then you would know that the work done by the gas would also have to be 6 joules, because once again we're keeping the change in internal energy at 0, so they have to be equal to each other. But one of the nice things is that we can use this to tell us what that is. And the area under this curve is going to be positive. In this case, I'm just making it up, but let's say positive 6. One question then is, what happens if you do the process backwards? What if instead of expanding the gas from 1 liter to 4 liters, we compress it from 4 to 1? Well, if that's the case, if you're compressing the gas, if you're taking this and you're making it into a smaller container, you're going to start those particles moving around much more rapidly, unless you cool it down. So what's going on in this case is that if you have compression of the gas and you want to keep the temperature the same, you have to remove heat. So it would look like the heat being removed in this case would be -6, the exact same value as up here, just opposite. And the work being done, I should write it actually B to A. B to A would be -6 joules as well. Now, bear in mind that the overall result of the internal energy and of the temperature is identical. Nothing has changed because we've stayed along the same isotherm. What has changed is what's doing the work. When you're expanding, the gas is doing positive work on something else, and to maintain its temperature, it needs to have heat added to it. If it's going this way, you're actually, those of you in calculus, you'll realize you're integrating from 4 to 1, which is going to give you the negative number, as opposed to integrating from 1 to 4, which is going to give you the positive number. But you're letting some other object do work on the gas. So basically, if this was the case where you're compressing it, the weight of these objects is greater than the force that the gas is applying, and so these are doing work on the gas. They're causing it to speed up, except for the fact that you're also removing heat at the same time. And that's sort of the trick of the isothermal experience. You take away as much heat as work you do to the gas, or you add as much heat as work the gas does, all to maintain the same temperature. Now, just briefly to look at another case or another example here. If we had a warmer isotherm, so let's say that this whole process was taking place at a higher temperature. Okay, and I know this is a higher temperature because for any given volume, the particles are applying a greater pressure. So they must be moving faster. They must have more energy in their collisions with the surface of the wall. And what you see is that if you go from the same spot, no, it's not quite the same spot here, the same spot over here, and let's say the gas is doing work, so we're expanding the gas. What you'll notice is that there is more area. There's not just this area, there's this whole area here, down underneath, okay? So there's more area, pressure times really the same change in volume, but we have a greater pressure that we're using. And with this expansion, the same amount of expansion though, at a higher pressure, that means that we have really, what it's coming down to is we have a greater force pushing over the same distance. So the gas is applying a greater force to the surface that it's pushing, and it's doing this over the same distance, which means at higher pressures, the gas is able to push harder and do more work. The converse of this is that if you have a gas at higher pressure and you're trying to compress it, so you're trying to get it to go this way, compressing the gas, you're going to have your work cut out for you because it's pushing against you much more vigorously the entire time. Especially towards the end here, it's going to get really tough because it's at a really high pressure. So you have to do more work in order to get it to compress because it's at this higher, it's applying a larger force because it's at a higher pressure. So those are the basics with your PV diagrams, and particularly your isothermal processes. Remember to draw your isotherms. That means that everything's at the same temperature along that particular line. And if you're compressing the gas, so going this way, then work is being done to the gas, and heat must be removed from it to keep it at the same temperature. If you're expanding the gas, your gas is doing positive work on something else, and you have to add energy to it in order to keep it at the same temperature. And as a general rule, if you're doing an expansion or a compression at a larger pressure, at a greater temperature, more work is going to have to be done.